Yes, we are live now. Please, you can start. We can see your entire system. So just take care.
Sure. All right, give me a second just. 1 second. Let me open the chat window. I hope this. Okay, that's all right. I mean, okay. So today I'll be giving a talk on like this deep learning course, and I'll try to answer all the queries which are posed by the students. I hope you can hear me now. Can somebody quickly confirm, like from the audience, if anybody
Yes,
is
sir, you're audible, sir.
okay? So I can see that like many people have posed certain questions. I have gone through all the questions. So what I'll do is like the queries which are common, I'll try to answer them first, and the queries which are like more individualistic, I'll try to take them afterwards. All right, just a second. So I'll need. Okay, so let me answer these queries one by one, regardless. 1 second, I need to, share another screen. 1 second, please. You can let me know if the other screen is visible. Yeah. 1 second. Okay. So I can see that like many people are asking about the backdrop derivation. So I'll start with a very basic introduction. Let's say that, okay, let's say that you have some data set with you. And in this data set, you have, say, maybe some images. Let me take a very basic example. So instead of images, let's say you have a data set, say about, say, some individuals who are suffering from diabetes. Okay. And our goal is to predict whether an individual has diabetes or not. So if you think about it, some of the features which could be relevant for predicting diabetes could be, say, the age, maybe, say, the BMI of the individual, could be, say, the height, maybe the gender. Okay. And say if there is, say, some kind of hereditary information, if it is available to you. So these are, let's say, some characteristics, okay, that you have captured. So assume that you have a data set where you have these as features: age, BMI, height, gender, hereditary information. And let's say you have this data about, so the first column is age, next column be gender, the third column, let's say it is height, the fourth column being let's say the BMI, and fifth column, let's say it's some kind of hereditary information, okay, which is captured in some numeric format. All right. So now you have some samples. So let's say this is individual 1, this is individual 2, and so on. So let's say we have 500 individuals in our data set. And my goal is to identify if this person is, let's say, if a given individual is diabetic or not. So I have this output column for every individual. And this output column tells me if the output is a 1, which means the person is diabetic. And if the outcome is a 0, which means that the person is non-diabetic. So you have some values about these different individuals. And in the output column, you would know the person is diabetic or non-diabetic. Let's say we have to implement this through a neural network. Okay. Now, one thing that you have, that you would have noticed by now is that we have a total of 1, 2, 3, 4, 5 features. So we have 5 features, and we only have one output to determine, right? So it is okay to say that this is a single output regression problem, right? We are trying to determine, oh, my bad. So it's a single output classification problem because we are trying to determine if the person is diabetic or not, right? The outcomes are discrete. Okay. So let us try discussing this data set like step by step, and how would you implement a neural network for it. So let's say that I am going to take, so first of all, in a neural network, you have say an input layer, right? And in this input layer, we are giving 5 features as an input, right? So we will have 5 nodes in our input layer. Okay. So the first node corresponds to age. The next node corresponds to the gender, and so on. Okay, one node for every feature. So think about this. So this is our input layer, and let's say we are trying to build a neural network with, say, one hidden layer. So let's assume that there are, say, 3 nodes in our hidden layer. So we have 3 nodes are in our hidden layer, and we have a connection from each of the nodes from the previous layer to the next layer. So let me call this as node 1. So node 1 will have a connection from, let's say, the 5 neurons of the previous layer to this node 1. Okay. Now you can imagine that there is a bias term as well. So the input to this bias is always 1. Okay, you can imagine that this is the bias input, the extra weight that we have, and there is a connection from this bias to node N1. Similarly, the case goes for node N2 and N3. So if you think about it, how can somebody tell me how many total number of connections would be there from the input layer to this hidden layer? You can answer me in the chat window. Yes, people. So if we have to compute the total number of edges from the input layer to the hidden layer, assuming it is a fully connected network, so every node in the next layer has a connection from the previous layer. So the answer would be 6 times 3, right? So we have a total of 18 connections, right? In the input layer, we have 5 connections plus 1 for the bias. So 5 plus 1 makes it 6. And from the 6 connections, we have, from the 6 nodes, we are having 1 edge each to the 3 nodes in the hidden layer. Let's say that, okay, now we have to predict one output, right? So we have to predict one output. And in order to predict this output, see, we are given a value 1 or 0, right? So we either have to predict if the value is 1 or if the value is 0. So if you have gone through the lectures, you would know by now, like whatever is the summation of these values, let's say if this value is A, if this value is B, and if this value is C. So if the incoming at this particular node is A plus B plus C, how can I squish this summation between 0 to 1? See, my goal is to ultimately predict whether the given classification, whether the given output is 0 or 1, right? So what kind of activation function will I use in order to squish the outcome, which is A plus B plus C, between a value of 0 to 1? So if you have gone through the lectures, you would know that it would be sigmoid. So sigmoid helps us to constrain the outcomes between 0 to 1. So sigmoid, if you know, is a function like this. So any value z, if you pass to the sigmoid function, it will shrink the values between 0 to 1, right? So now let's say if we have this structure and let's say I want to determine the weights. Okay, if we have this structure and I want to determine the weights, oh my bad. So this would be 0 to 1 included. Okay. So now let's say if we have this structure and we want to determine the weights. So let me name these weights. Okay. Let us say the weights from the input layer to the hidden layer, they are, let's say, W1. So W1 is essentially a matrix. Okay. So W1 is a matrix. Let me instead call it as a column vector. Okay. So W1 is having the weights from the input layer to the hidden layer. Okay, these are the weights from the input layer to the hidden layer. So we have a total of 18 different weights. Right, it's a column matrix. We have a total of 18 different weights here. Similarly, if I say that the weights W2 are from say hidden layer to the output layer, so this is called as the output layer. So let me say W2 are the weights from your hidden layer to the output layer. So there would be, if you think about it, let's say if I have one bias term here in the hidden layer, right? So how many total weights would be there in the hidden layer? From hidden layer to this output layer, how many total weights would be there? Anybody? You can write it in the chart window. So the correct answer to that would be 4 into 1, because you would have a connection from bias to the output as well. So there would be a total of 4 different weights. Now I have to determine these weights, right? I have to determine these weights. So let me try, okay. So let me try explaining like what happens, okay? So in the feed forward step, see in the feed forward step, so let's say if you're looking at the feed forward step, so we have this neural network, right? So what is going to happen? So let me draw the biases in red, okay? One second. So I'm going to target only one. Let me target, let's say, so this is 1, the bias is 1. Our bias is 1. Let's say that for the first individual, if you look at the first individual, the first sample, if I use, let's say the values are A1, A2, A3, A4, and A5. If let's say these are the 5 values in your data set, you have the values as A1, A2, A3, A4, and A5. Let's say the weights are W1, or rather, let me say, yeah, this is fine. Let's say this weight is W0, W2, W3, W4, W5. So I am interested in computing what I'm going to get at this particular node, let's say N1, right? So you guys would know by now that I will get 1 into W0 plus A1 into W1 plus A2 into W2 plus, let's say, up to A5 into W5. So each input is going to be multiplied with the corresponding edge weight, right? All right. So at this particular node N1, let's say I have some activation function. So see there, I mean, many of you have asked like what kind of activation functions can I use? So there are tons of activation functions. So let me talk about first, like what are the different possibilities of activation functions. So if you think about it, I mean, you would have used sigmoid. So sigmoid is nothing but, as we have discussed already, so this is nothing but 1 upon 1 plus e to the power minus z, where z is the input to the sigmoid, right? And it squishes the range between 0 to 1, right? Now you have, let's say, rectified linear unit. So rectified linear unit, if you know, what it will do is, let's say, if let's say if your input z, so let me say the function is z, okay, so the function z will be outputting the value z if z is greater than 0, right? And what you can say is that it is 0 if z is less than equal to 0. So basically what it does is it does not encourage any negative gradients at all, right? So any input which is coming, and if you applied Relu on top of it, so if the value is negative, it will make it 0. Otherwise, the value, if it is positive, it will be retained as it is, right? So if you think about it, Relu function has a curve like this. Okay, so if you are drawing z here and fz here, okay, so you are saying that if the input is negative, the answer is 0. Otherwise, the answer is like whatever the value of z is, considering z to be positive. Okay. Now you have other variants as well. So you have different variants of Relu as well. So for example, you have Leaky Relu. So you can, so this particular variant of Relu, it encourages some negative gradients. Okay. It encourages, let me say, some negative gradients. Okay. It doesn't allow everything to pass as it is. So what is happening is like this. Okay. So if some value is negative, okay, so let me just write it first. Okay. So let's say, so fz is equal to z if z is greater than 0. Okay. But what happens if z is less than 0? Then it is multiplied with some constant factor alpha. Okay. And this constant factor is a very small value. It's a very small value. Okay, it's a constant which you are multiplying. Okay, it's kind of a hyperparameter which you are multiplying with the input z, just to ensure that if this z is negative, this this negative value is squished, or it is like you can say constrained to a very small negative value. Okay, however, it is not going to 0, unlike in Relu. Okay. So this is about Leaky Relu. Now you have other variants like exponential linear unit. So exponential linear unit is another kind. I mean, let us move ahead and instead. So you can think about hyperbolic tangent. You can even think about a step function. Okay, but you have to. If you are thinking of picking up, let's say, any of these activation functions, can somebody tell me in the chat window, like, why do we pick a specific kind of activation function? What is the reason behind it? See, one idea is, if you are picking a specific kind of activation function, you would want your differentiation to become easy, right? The first thing is, like, if you're trying to solve for the partial derivatives, those partial derivatives can be easily computed if let's say if you pick sigmoid or Relu. It is very easy to compute. Even with Leaky Relu, you can say that the gradients, if you compute the derivatives, if you compute, it becomes really easy to compute. So we take these activation functions like for mathematical simplicity. And what's the most which is the most important reason for picking up an activation function? And the answer to this is non-linearity. See, we want to induce non-linearity in our network. Okay, let me ask you this question. So I'll make a figure. Okay, so look at this figure. Let's say I have certain neurons, okay, in the input layer. So this is my input layer. So this is my hidden layer. So let me say this is my hidden layer 1. Okay. You can have, let's say, some more hidden layers. Let me say hidden layer 2. And you have, let's say, a few other hidden layers. Let me say there are some X number of hidden layers. Okay. And now, let's say we are interested in determining one output, and this is the corresponding output layer. The question comes, one second, Shamila, can you mute yourself? Yeah, thanks. So the question is, let's say that you have connections from this input layer to hidden layer 1. Hidden layer 1 has further connections with hidden layer 2. And imagine that it's a fully connected network. Okay, it's a fully connected network, but with no activations. So there are no activations in the hidden layer. So in any of the hidden layers, you do not have any activations at all. So my question to you is, do you think I can squish this entire network into one neural network which only has one hidden layer? So think about this question. So you can assume either, let's say, the identity activation function, which means that whichever value is coming, so it is, I mean, you are just returning the same value which came as an input, okay? Or you can say that there are no activations at all, okay, in the hidden layer. Is it okay to say that I can convert this whole neural network into just one hidden layer? Okay, so if this is the input layer, I only need one hidden layer, and obviously the output layer is there. What do you think? Is the answer yes or no to this question? You can reply it in the chat window. Yes, people, what do you think? So can we convert the previous network into this network with one hidden layer? I hope the question is clear. See, and the answer is yes. See, the idea is, if you do not use any activations in the hidden layers, or if you use identity function as the activation in the hidden layers, whatever is incoming. So let me just do it for a simple, simple example. Okay. So let's say this is hidden layer 1 and this is hidden layer 2, and this is output layer. Okay, let me try to prove it for this network where you have let's say A and B. So this is, let's say, the input layer. Okay, let me just use 2 neurons. So let's say this has weight W1, this has weight W2, this has weight W3, and this has weight W4. Okay, so what I'm trying to say is I can convert this network into this, okay, where I will have only a single hidden layer. I can basically squish, like how many, depending on like whatever number of hidden layers that you have, everything can be squished into one hidden layer. Okay, and the reason is this. Look at this. So let's say this input is A, this input is B, or let me make the inputs as A1 and A2. Let's try to see what do we get at this particular node. So if we look at this node, we get A1 W1 plus A2 W2, right? And now, if you think about it, what do we get at this? What do we get at, let's say, this node H2? So this would be nothing but you are going to multiply this with W3, right? Now, can I write this whole thing? Can I write this whole thing? And if I multiply this with W4, this is what I'll get at the output layer. Yes or no? Because you are just propagating whatever you get as an input to one node. You just propagate it as it is. Now, look at this, what we have over here. So what I'm going to do is I'm going to expand this. So I can write this as W3 A1 W1 plus A2 W3 W2. Now what I'm going to say is that, see, W3 W1 is another constant, or let me say another edge weight, So you can imagine this. So A1 is multiplied with W3, W1. Okay. So this is now the new edge weight. Okay. And if you see this, this is nothing but this is W3, W2. And now this weight, this final weight, it remains W4. So did you see that we were able to squish two hidden layers into one hidden layers like this? So this process can be extrapolated to any number of hidden layers. And why is this happening? Because there is no nonlinearity in these hidden layers, right? So you can say a neural network with, let's say, some number of hidden layers. If you don't have an activation function in those hidden layers, it is as good as having a neural network with a single hidden layer, right? So that is another, purpose of introducing like activation functions which cause non-linearity, right? Okay. So I hope the feed forward step is clear to you. Now let's say we have to talk about the backprop step. So let me make my network smaller by a bit. Let's take let's say one value only in all the layers. Okay, and let's try to find out the backprop weights. Let's try to figure out the like weight update equations for the different weights that we have. Okay, so let's say that this is our input. Okay, I'm going to use one node only. Okay, let's say this is the first hidden layer. Let me say H1. We have, let's say the second hidden layer, we have H2. You can extrapolate it to like as many, I would say as many hidden layers as possible. But let us try to, okay, let us try to do it for a simple task. Okay, let us try to do it for a simple task. And this is our output layer. Okay. Let us try to induce some kind of nonlinearity at hidden layer 1 and hidden layer 2. Let's say these are sigmoids. Okay, let's say these are sigmoids. So if I say that if x1 is getting in the input, okay, so let's say this node has, this node gives you an output A, okay, multiplied with W1, and you get Z1 here, okay. So at the output of this node is A, okay, which is multiplied with W1, and the input to this, you can say a node, okay. So let me say this is A1, this is W1, this is Z1. So A1 is the output of, say, this node N1, okay. So A1 essentially is nothing but X1, right? Because there is no non-linearity, there is no activation function at the, at this node N1, right? We do not apply any activations at the input layer, right? Let us think about what Z1 is. So Z1 is nothing but Z1 is the input of this node N2. Okay, Z1 is the input of node N2. And what is Z1? Z1 is nothing but, you can say, W1 times, so A1 times W1. I hope you will agree with this. So whatever is outputted by node N1, you are going to multiply with the edge weight, and then you get A1 into W1 as Z1. Okay. Now let us talk about A2. So A2 is nothing but output of node N2. And A2 is nothing but sigma times Z. So sigma times Z1, or you can call it as sigma times A1 W1, right? Similarly, if you think about, okay, let me just complete this. So this is W2, this is Z2, this will be Z3, okay? This will be W3, let's say this is Z4, okay? And at this node, let's say, at this node, let's say we are going to, so let me revise the example a bit. Let's say right now we are doing regression, okay? Regression will be fairly easier to solve. Okay, let's say we are doing regression. So at this output node, we do not have any activation function because we are doing regression. Okay, so there is no activation function. So what we get is Z4 is the final output. So if you think about Z4 is nothing but, my bad, let me call this as A3. So Z4 is nothing but A3 into W3, right? And because there is no activation at the output, so Z4 stays like this. Okay, you can say that the output for this sample, if I call this as Y hat, this is going to stay the same because there is no activation function on the output node. Let me just complete this. If you look at this node, say N3, so for this node N3, the input is, if you look at the input is Z2. Oh, sorry, yeah, the input is Z2, which is nothing but A2 into W2, and the output is sigma times, the output is A3, which is nothing but sigma times Z2. Okay, I hope this part is clear. Okay, let us try to figure out the edge weights W3, W2, W1. Okay, let us try to figure out the weight updates to these W1, W2, and W3. So before figuring out these weights, can somebody tell me, if my task is regression, what kind of loss function should I use? If my task is regression, what kind of loss function should I use? Yes, people. If the task is regression, which is the loss function that I should use? So see, you can use any of the loss functions, let's say mean squared error, root mean squared error, log mean squared error. But the idea is that function has to be differentiable. Okay, so let us use, let's say, mean squared error. Okay, let us use mean squared error, and mean squared error, as you would know, is nothing but the predicted value minus the actual value whole square, right? And let's say if there are n examples, one second. So if there are n examples, so you can divide it by n. So you can see that you are taking the sum of square differences between the predicted and the output values, right? So this gives us the mean squared error, right? Let us try to use this mean squared error. So let me call this function, let's say, as my loss function. So let me call this function as L. Okay, so this is my loss function L. And let us try to update these weights W. Okay, W3, W2, and W1. Now, why this algorithm is called as back propagation? The reason for that is you first move from output to the, I would say, to the last hidden layer. Okay, so in the feed forward fashion, you were moving from the input layer to the output layer, right? From the input layer to the first hidden layer, then from that first hidden layer to the next hidden layer, and so on. Back propagation is just the reverse for it. So here you are doing the recursive opposite of what you were doing in the feed forward fashion. Okay, so what we are going to do is we are going to differentiate this L with respect to W3. Okay, so in order to find, let's say, the gradient that is caused, that is with respect to this weight W3. So let us try to figure out the gradient for that. Okay, so I'll make a small change. Okay, I'll make a small change. So instead of using, let's say, mean squared error, what I will do is I will use this rather. Okay, which will make our calculations very simple. So instead of 1 by n, let me say that I'm using 1 by 2. And the reason for that is, see, when I take the derivative of this, okay, this 2 is going to come out and I can easily cancel this 2. Okay, so you can have as like whatever loss function that you deem appropriate. But the thing is that we have to ensure that I mean, the derivatives can be easily figured out. So I'm going to use a 1 by 2 here. You can also go with 1 by n. It's not going to create a problem. It's just that you will then have 1 by 2n in the gradient of this function L. Okay. All right. So let us try to differentiate this. So if you see, what I'm going to get is 2 times summation of yi hat minus yi. Okay. This is what I'll have. And I have to take the derivative of yi hat minus yi with respect to w3, right? There is a 1 by 2 also outside, so you can cancel this out. So this part stays as it is. Now I have to worry about this. Del yi hat minus del yi, and we have to we have to differentiate this with respect to partially differentiate this with respect to the w3 weight. Okay. So we have this term. So I'm going to, let's say, write this term as, let's say, a. Okay. Or rather, let me say use some constant c. Okay. So this is going to be a constant. Okay. Let me say this term is, let me call this term as b. Okay. Capital B. So this is this term. So b into, we have this to solve. Okay. With respect to w3. Now look at this yi hat. Okay. Look at this y hat. This is a3 times w3, right? If you remember, a3 is the output of node h2, and then it is multiplied with the node w3. So I can just replace b times del of a3i into w3 minus yi, okay, divided by del w3. Now I can, because it's partial differentiation, I can do it for the individual terms. So del of a3i into w3 divided by del w3 minus del of yi divided by del w3, right? So this term goes away because it's a constant for every output, right? It's the actual output value. So this derivative would be 0. What would be the derivative of this? It would be nothing but b times a3i. It would be b times a3i. So this would be the derivative. So let me just write this derivative again. So we have our loss function L, and we want to see the derivative with respect to w3. So this would be I equals to 1 to n y hat minus yi into this a3i. So this is the gradient with respect, a gradient for the weight w3. Okay. I hope you guys know about gradient descent. So if you know about the gradient descent update equation, so the gradient descent weight update equation is given by, it's given as, let's say, for any weight wi, let's say I'm trying to find the new weight, new value for this weight wi. It is given as wi old minus learning rate times the gradient. So gradient is, remember this gradient is with respect to this wi. Okay, gradient is with respect to this wi. Okay, so if you look at this, so if I say, if I'm starting with some value for w3, let's say I'm starting with some random value for w3, which is, let's say, 1.4. So if I'm starting with some random value for w3, so let's say I'm doing some random initialization for w3, and let's say the random initialization value was, say, 1.3. So how do I figure out how to change this w3? So what you can do now is, you can do this as, so the new weight is nothing but 1.3 minus learning rate. Let's say you fix, so you have to decide what the learning rate would be. Let's say this learning rate is 0.01, okay, 0.001, okay, multiplied by the gradient. This can be computed in the feed forward fashion. So this is your gradient, right? So I can just write this as del L by del W3. Okay. So you can just compute it in the feed forward fashion, and you'll be able to compute what is the new weight for W3. Let us try to do it for W2. So now we have to do it for W2. Okay. So if you want to do it for W2, remember, okay, if you remember, L was 1 by 2 of yi hat minus yi whole square. Okay. We were trying to do it with this instead of mean squared error. Okay. So if I want to differentiate this with respect to W2, the first thing that you will get is summation I equals to 1 to n. Okay, I'll just write, I'll try to be quick because of limited time. So what I'll do is I'll write it very quickly. Okay, this becomes yi hat minus yi. Okay, 2 gets cancelled out, right? This 2 and this 2 gets cancelled out, right? And then we have to differentiate yi hat with respect to W2 minus yi with respect to W2. Now, if you think about it, this is 0 because it's a constant. The only thing that we have to worry about is this, right? And now let us try to substitute what yi hat is. Okay, so let me call this thing as b. Okay, yeah, we should only be worried about this term. So look at this del of yi hat with respect to del of W2. Okay, so if you remember, see, this y hat is nothing but W3, A3 into W3, right? If you remember. So if you remember, this yi hat is A3 into W3, right? And let us try to see what A3 is. Okay. So if you look at A3, A3 is nothing but sigma times W2 A2. So if you look at A3, one second, I'll just highlight it. So if you look at this term A3 is nothing but sigma times A2 into W2. So you can just replace A3 there. So this becomes sigma times A2 into, my bad, A2 into, I guess, W2. Yeah, A2 into W2. So A2 into W2. Okay, and W3 divided by. So this we have to solve, right? Now, because we are doing partial differentiation, this W3 can be taken out. So this becomes W3 delta of sigma of A2 W2I divided by sigma of W2. Okay. Now, see, if you know, see, let's say if I have this function fx and the function is the sigmoid function. Okay, and let's say I'm trying to take the derivative of this function with respect to this x. Okay, so I'm trying to take the derivative of this function with respect to x. I'm not sure whether you have done this derivation or not. This is very easy to derive. This will turn out to be sigma into 1 minus sigma if you take the derivative of it. And obviously there would be a dx by dx. So let's say if this value was let's say some 5x, right? So this would be d times, so this term would be d times 5x by dx, which would turn out to be 5. Okay, so you just need to remember this. All right. Okay, so I'm going to use the same thing here. Okay, so now we have to differentiate this component with respect to W2. So you can see that whatever this term is, right? If you want to differentiate this, you are going to get A2W2I into 1 minus A2W2I, right? If you take the differentiation of it multiplied by derivative of A2W2I with respect to, multiplied by the derivative of A2I, I've put the I at the wrong place. So this I should be in A2. Okay, so A2I into W2. This should also be, I should be here. Okay, my bad. It should not be there. Okay. Okay. So this is what we are going to get. And finally, we have to derivate this, take the derivative of the remaining inside portion with respect to W2. And what do you see? You are going to get this, right? So you are going to get, so let me take the final derivative. So we have the term B, okay? We have the term W3. We have the term A2I W2. So A2I W2 into 1 minus A2I W2. Okay. Sorry, my bad. 1 second, I'll just rewrite this. I'll just rewrite this again. And I'll do it on a separate page. So we have to take the derivative of this term. Derivative of sigma of A2I W2, A2I W2 with respect to del W2. With respect to del W2, so this would be sigma of A2I W2 into 1 minus sigma of A2I W2 into del of A2I W2 divided by del W2, right? And now if you look at this term, so only A2I would remain. So this would be A2I into sigma of A2I W2 into 1 minus sigma of A2I W2. So this is your gradient multiplied with the term B, and B is nothing but yi hat minus yi. Now this becomes, so if you are using the gradient weight updates, so if you are using the gradient weight updates, this is the gradient with respect to W2. So you can say that W2 new is equal to W2 old. So whatever is the previously initialized value, you are going to multiply the learning rate with the gradient and then subtract it from it. Okay. So this is the gradient with respect to W2 that we have computed here. This can be computed in the feed forward fashion. So compute this in the feed forward fashion. Multiply it with the learning rate. Subtract it from the previous value, you will get to the new value of W2. Similarly, you can do it for W1. And you will see that, there would be a lot of, so if you observe this, let me just show you the gradient weight update. So try to observe the gradient weight update for this. Okay. Look at this. So this is the sigma of some term. This is again 1 minus sigma of some term. Okay. So if you remember, see, sigma squishes the value of any input between 0 to 1, right? Similarly, if this is some value between 0 to 1, 1 minus whatever this value is between 0 to 1, so this will also be between 0 to 1. I hope this part is clear. So if sigma of some value is between 0 to 1, if you take 1 minus sigma, that will be again a value between 0 to 1, right? Now, hear me out. So look at the gradient weight update equations. So let's say you're trying to do the gradient weight equation for, say, W3. Can you think what is going to happen if you have a large number of sigmas? What is going to happen if you have a large number of sigmoid multiplications in the gradient weight updates? See, if there is a term, so see, sigma is a value which is between 0 to 1, right? You are multiplying it with another value which is, say, between 0 to 1. And if you have a large number of such values, the product will actually shrink. Shrink to 0. With a few of these multiplications, right? And this is what is called as the vanishing gradient problem. So this is to give you the intuition, like why you should not use sigmoid and maybe use some other activation function like Relu or some other variant of Relu. okay, because it can lead to vanishing gradient problems very, very quickly. So Lakshman is asking, should we need to remember the complete derivation, or is it enough to understand and use? See, Lakshman, my perspective is like, you don't need to remember the whole derivation, but you should know like how the partial differentiation is coming into the picture, what are the different kinds of loss functions that you could use, okay, that you need to know. What are the different kinds of activation functions, okay, what are the pros and cons for them. I think that that would be more than sufficient, okay, if you are only worried about the implementation part, okay. This is regarding the questions pertaining to back propagation. So similarly, you can derive the weight update for, say, W1. Okay. Similarly, you can derive the weight update for this W1, the first parameter W1. Okay. Rest stays the same. Okay. Now, many of you have asked me, like, can you give us some resources to read, okay, or maybe to refer. Okay, so let me show you very, very quickly. So Meenakshi, are you there? Are you there in
Yes,
the?
sir.
Okay, Meenakshi, is there a possibility that we can share, let's say, some material with the students?
Sure, sir. On the discussion forum, we can share.
Okay, so I have prepared a small Python notebook because many people had asked me like how to actually implement these neural networks, because I mean, there is very little on the implementation side in our course. Okay,
Okay, sir.
all right, so I'll share a very preliminary introduction. All right. One second. Meenakshi, can you please let me know if the screen is visible to all?
Yes, sir. It's visible.
Okay. So guys, I'm going to show you like how you can actually implement these neural networks in one of the deep learning frameworks. Today I'm going to use Keras, but you are, I mean, more than free to explore, let's say, PyTorch, Caffe, even TensorFlow. Okay, so it's up to you. But today I'm going to show it to you in Keras. So I've built a sample Jupyter notebook, which I'll share with all of you. So you can go back and refer to the code and try making changes to the code. Try to tune the hyperparameters to get to the best results. Okay. I have shared the URL link for the dataset that I'm using today. So this dataset, let me describe. So this is the same dataset I was talking about. Let's say I have the data about some individuals, and I want to predict if these individuals are having, I mean, if an individual is suffering from diabetes or not. So there are a total of 8 features: age, number of pregnancies, if the person is the female, okay, glucose, blood pressure, skin thickness, insulin, BMI. Diabetes pedigree function is the hereditary function that I was talking about, okay. And the outcome tells you if the person has diabetes or not, okay. So what I've done is I've taken the features and the output separately. I've split my data into X and Y, and now I am making a neural network. So this is where I mean the neural network part comes in. So what you need to do is, I mean, there are 2 ways to create a neural network. You can either import the sequential library, or you can import the functional library from Keras. Okay, I'm using the sequential library, and I'm trying to build a fully connected network. So if you want to build a fully connected network, I mean, a fully connected layer is also called as a dense layer. So that's why I'm importing this dense layer. Okay, so this is how the model starts. Okay, so you call the sequential library, and now you can add the dense layers one after the other. See, if you remember, we have a total of, if you think about this, we have a total of 8 features, right? If you go back, you read this. So we have a total of 8 features in our data set. So we have to decide, I mean, we have to make a network with 8 dense, 8 nodes in our first dense layer. The second hidden layer has 6 nodes. And the last layer has only 1 node, because we are trying to classify if a particular user has diabetes or not. So there are many optimizers that you can compile this network with. So you would have heard about stochastic gradient descent, Adam optimizer, Adagrad optimizer, RMS prop optimizer. There is a dedicated discussion in the video lectures about these. Okay. Now, because it's a classification problem and specifically binary classification, so you can use the binary cross entropy, loss. If you were using, let's say, if you were having a multi-class classification problem, then perhaps you can use the softmax function here. Okay. And I'm now fitting this to my data. The X train is my train data, the training features. Y train is the corresponding labels. I'm using the batch size to be 10. So this is stochastic gradient descent with a certain, this is Adam with this specific batch size. Okay. And the number of epochs are 100. Okay. And you can see that, one second. As of now, my accuracy is 74.78% on the training set with just 100 epochs. Okay. So what I did was I tried computing the accuracy for my test set as well. And it was, fairly close. So when you'll go through the lectures, you will understand the concepts of overfitting. So you can actually determine by looking at the test accuracy or the validation accuracy at different epochs to determine if the model is overfitting. So you can compare the changes in the test accuracy over the different epochs, and you'll be able to figure out like whether the model is overfitting or not. And you can stop at that point where the model starts to overfit. So just stop before that point, right? So you can get the best accuracy at those points. So just for a comparison sake, I have implemented the other classifiers as well. And I wanted to show you like a neural network with just 100 epochs, okay, with just one hidden layer, okay, is able to do as good as like these traditional classifiers. So it is lying somewhere here. Okay. So it is better than this k nearest neighbors. But I have tried figuring out like the optimized values for these different classifiers. And I found that, neural networks with just one hidden layer, I haven't even, fine-tuned the number of neurons in that hidden layer, and it can actually do pretty well. Okay. So if you think about increasing the number of hidden layers, you can actually easily, I would say easily get better results than the ones that you get with traditional learning algorithms. Okay. I have a code for the regression task as well. So what I did was instead of actually predicting if a person is diabetic or not, I used all the other columns as my features. And now I'm trying to predict the BMI of the individual. So BMI is a real valued feature. So accordingly, I created the same, neural network. Okay. And now if you see, I have 13 nodes in my first hidden layer. And the input layer has a total of 8 features. Okay. The next hidden layer has 6 neurons, and the output layer has only 1, because we are trying to predict only one output, which is the BMI, which is a real valued variable. So this time I compiled the model with mean squared error. The optimizer stays the same. You can try with different values of the optimizers. And I found that the results on my test set, they were not that great. So there was an error of close to 54. You can try working on this, have more layers. Okay. Feed in more data. As of now, I'm only using, I think, 70% of my data. And keeping 30% for validation and 30% for test. So I think from the train set itself, I'm taking in 30% of the train set as my validation set. So even though they are distinct, I just take a subset of my training set to do the validation. But then, the number of samples in this data set is just, I think, 750, close to 768, if I'm not wrong. 1 second, let me see. Yeah, this data set has just 768 entries. Imagine, let's say, if you have, close to say 1500 examples, you can easily reach to accuracies like 90-95%. So this is like how you would implement neural networks in Keras. So a few key takeaways are, so let's say if you want to have a multi-class classifier where you have multiple classes, all you have to do is change the number of units in the corresponding output layer. So if you have 10 classes, make the number of units to 10. So you can just change this to 10, and the rest everything stays the same. So I'm going to stop here and If there are any questions, I can take them up.
Sir,
Yes.
sir, in a gradient descent method, we assume that the loss function is a convex function of the parameters which we are trying to learn. So, are there other methods in which like loss function is not a convex function, like it does not have a minima or have several minimas?
Okay. So see, when you talk about, let's say, mean squared error in terms of regression, right? With respect
Yes,
to
sir.
neural networks, the function is not convex. Okay. If you think about doing linear regression, then the function is convex because the output, the input which is coming from the, from the different neurons, it has non-linearity, right? Yes or no?
Yes, sir.
So once you have activation functions in your, I would say across the hidden layers, then the function is not convex anymore. Even if you use, let's say, a mean squared error in the output layer. Okay.
Yes, sir.
The advantage of gradient descent is that if you do different initializations, if you, let's say, if you start with different initializations, you may end up figuring out, let's say, which minima is better, right? You can always look at the error, start with different initializations, and whichever initialization gives you the least loss function, the least value of the loss function, that is the best minima. But I cannot say for, say it for guarantee that the minima that you'll obtain will be the global minima, because there can be many such points, right?
Yes, sir. Yes, sir.
Okay.
So, sir, we have to initialize several random. We have to start with several random
Yes.
parameters. So to
No, you
reach.
have to think about, let's say, start making multiple neural networks. Each neural network has its own initialization. Okay. But there is some research along these lines, and they have said that if you are doing so there are actually heuristics for deciding like how you should initialize your neural networks, and if you follow those heuristics, okay, then whatever minima that you get would be very, very close to the global minima. Okay. So instead of just doing plain random initialization, you can do initializations from a uniform distribution, okay, or from a specific range. Okay. Then there is something called as Healy initialization. uh, so when you'll go through this course, you will understand like the different initialization techniques, and also you will learn like how to tackle like problems, like how to avoid minima with a non-convex function, how to get to the global minima with a non-convex function. See, otherwise, if you train one single neural network, if you do not have the resources, training one neural network can take many days, right?
Yes, sir.
So I hope this answers your question. So you
Uh,
need to start with
yes, sir.
base initializations, and then, but there are very good heuristics where you can, if you start with those, you will certainly end up in having a good minima, good local minima.
Okay, sir. Thank you, sir.
All right.
Hello,
Yes.
sir. Am I audible?
Yeah, you are.
Yeah, sir. Good evening. Thank you for the excellent session, sir. Sir, I just wanted to ask if in case of CNN, how can we go for K-fold or different types of cross-validation methods like leave one speaker out? How can we go for it?
You can do that, but don't you think training a CNN with multiple train and test sets, with multiple training sets, don't you think it's going to cost you a lot of time?
Yes,
So
sir.
you can actually do it with the K-fold method in sklearn. So you can make a wrapper and call your classifier and do cross validation with that. But the part which will frustrate you the most is like the time taken to train each model, right? Every fold you'll be training one model, right?
Yes.
And every fold you'll be running multiple epochs. So
Yes.
when we talk about these neural networks, what happens is like instead of doing k-fold validation, what people do is they will give you a train set and a test set, and they will fix one train and one test. They will not make multiple train and test sets, unlike in traditional algorithms. Okay.
Yes.
So what you can think of is that you can always use some heuristics to to talk about like I would say, first of all, the different kinds of activation functions, different initialization techniques. So, I mean, it comes with experience, but if you start training multiple neural networks, I mean, it's going to consume a lot of time, right? There are no two
Yeah,
ways
yeah.
about it.
Yes. Means you want to say that we should try different initialization methods and different optimizers.
No.
And
I'm saying that if some heuristic has worked for you in the past, go with that. Okay, so let's say out of the different initialization techniques that you have studied, if you used, let's say, any one of them and which gave you the best result, so try with that. See, if you exhaustively figure out what is the best initialization technique, let's say there are 10 initialization techniques and you're trying to figure out the best amongst them, you'll have to train 10 networks. Do you agree?
yes.
Yes or no? See, I am
Yes.
not even considering the hyperparameters with each of these initialization techniques. There can be many hyperparameters with each of them as well. So for each of them, you would have to look at, I mean, you have to do a grid search within each of them. Okay. So that is why what people do is they take pre-trained networks, okay, which people have trained on, let's say, some other data set, and they reuse those networks and they try to fine tune those networks on the data set that they have. Okay. So imagine that, let's say, you are using a pre-trained network which is trained on, let's say, some image data set. Okay. So this image data set may have 1,000 classes. Now, if you have a data set where you have only one class, so what you're going to do is you're going to retain all the weights as it is, except for the output layer. So you are just going to have one output or one neuron in the output layer. So replace that output layer with a layer which has only one neuron and retain all the other weights as it is.
Yes.
Okay. Otherwise, it's going to take you a tremendous amount of time just to train these networks with different. I mean, there are so many hyperparameters, right? This is the bottleneck with deep learning.
Yeah. Yes, sir. Thank you, sir.
All right, Swati.
Good evening, sir. Am I audible?
Yes, you are audible, Mrityunjay.
Sir, one question I have, as you use the term fully connected network, and so I assume that there must be a scenario wherein you would be using the not fully connected
Absolutely.
artificial neural network. So in what scenario we need to use the fully connected, and when in what scenario not fully connected?
Okay, so think about this. Let's say you have a very big network, which means that you have a large number of hidden layers. Can you think in terms of the number of parameters that you'll have if I start increasing the number of hidden layers? They will go on exponentially increasing.
Yes, sir. They will be very complex.
Right. So what if I want to train a very deep network, but I do not want to have those many number of parameters? What can I do?
Then we partialize.
Then we can say that I do not have to connect every node in the previous layer to every node in the next layer. Maybe I'll have a few connections. Have you heard about techniques like dropout and others?
Not, sir, not yet.
Okay. So you'll learn in this course that, so see, there are techniques where you don't have to start with, let's say, always a fully connected network. But if you are doing that, it is going to take you a lot of time because there are so many parameters. You must have come across CNNs by now, right? Convolutional neural networks.
Not yet, sir. I am in third module yet. So
okay. So if you let's say start with that, you'll realize that CNNs were actually introduced just to avoid having a large number of parameters in the fully connected layer.
Okay.
And that was one of the reasons why CNNs were introduced. Another reason is like they also exploit spatial similarity. But then the primary motive was to minimize the number of parameters in the fully connected layers.
Okay, got it.
All right.
Thank you.
But you can always have like whatever connections that you want from the previous layer to the next layer. It is just that you would have to build a custom network then.
Okay, is it like, sir, in the decision tree we do the pruning after making the complete decision tree?
You can also do that. Think about, let's say, dropping off those edge weights, okay, which are having the absolute values of those weights are, let's say, very, very close to zero. So they will never be making I would say a significant contribution to predicting the output. So you can always drop them.
Okay, sure, definitely.
Okay. So that's one idea, but this idea is like, this is done after training. Okay.
Okay. Yeah.
But instead of having, so what I'm trying to say is like, instead of connecting all the nodes of the next layer with all the nodes of the previous layer, you have like whatever connections that you want. Okay. You don't have to connect everything with everything, but then you would have to make a custom model, because you have to find out the gradient weight updates. Because see, whatever these people have implemented in these, let's say whatever Google people have implemented in Keras and PyTorch, okay, they are dedicated for fully connected networks and convolutional neural networks. Okay. If you want to make your own network, you would have to come up with your own gradient weight updates, right? You have to make a function for that. You can also do that. Okay. You can create custom models.
Okay. So for the person who is not very competent in the programming, so they are using the Keras and TensorFlow. So we assume that they have the fully connected layers.
Yeah, you can assume fully connected layers. You can assume CNN layers. But then if you want to make your custom model, you would have to be a little more well versed with these frameworks. Okay.
Okay.
So you can use a TensorFlow and a PyTorch for that. Keras will not give you that much capability.
Fine.
All right.
Thank you for it. Thank you.
All right.
Hello.
Yes, Swati.
Sir, I'm having one more question. Actually, if I'm using a pre-trained network, in order to check how that model is performing, there are different parameters we are considering, such as precision, recall.
Yes. Go on. I lost you.
Yeah. So can you please elaborate what is the process, how we can save that, and how we can calculate this MAP in short, if possible?
Okay. So see, the idea is very simple. I would advise you to go and explore sklearn.metrics. Okay, there is this library which is called as sklearn.metrics.
Okay.
Okay, so whatever metric that you want to compute, okay, let's say you want to compute a metric which is, let's say, computing the difference between the actual values and the predicted values for a regression task.
Yes.
So what are the different possibilities for it? One could be mean squared error. One could be sum of squared errors. One could be mean absolute error. So there are actually many, different kinds of metrics which you can use. So let me just show you like the different metrics. Let me show you the regression metrics. There is actually a ton of metrics that you can use. So max error, mean absolute error. You can just look at the documentation.
Okay.
Input the whatever you require. Pass the actual and the predicted values, and it will do the job for you.
Okay.
Okay. This was your question, right? Or were you asking something else?
Yeah, actually, I'm working for multiple object detection.
Okay.
So in order to check the accuracy of that, I need to check. I'm using a COCO data set. So I'm having different 80 classes. But finding out the ground truth image of all 80 classes, and then finding out IOU, that particular method I'm finding little bit difficult.
Intersection over union is there in sklearn.
Okay.
You can directly use it.
Okay. Fine.
All right.
Okay. Do you suggest any good annotation tool for this?
Then I have only used this label IMG is there.
Label IMG.
Yeah,
okay.
Which is used with YOLO. I have used that.
Okay.
So,
okay.
I don't know of any other tool. I only use that particular tool.
Label IMG, right?
Label IMG, yeah. That does the job for me.
Okay. Thank you so much, sir. Thank you.
Yes. So if there are no other questions, I think we can end the session. Or you can let me know, like, okay. I don't see any questions in the chat window either. All right, then, Meenakshi, can we end the session now?
Yes, sir.
All right. So will you be doing it from your end, or do I have to do it from here?
We can leave the meeting, sir. This will be done by the NPTEL
people. Okay. All right. Yes.
Excuse me, ma'am. Will be sharing the recording of this session?
This will be available on the NPTEL portal itself, ma'am.
Okay. Fine. Thank you.
Sir, actually, I have a question. Can you please share that code that you demonstrated? So that
Sure. 1 second, please. 1 second. Yeah, go ahead. I hope this is visible to you.
Yes, sir, it's visible. The code, can you share it, sir?
Yeah, definitely. I'll share it in the discussion forum.
In the discussion.
Yeah, we'll do that.
Okay, sir. Thank you.
All right. All right, Meenakshi, I'm leaving the meeting. In case, guys, if you have any questions, you can always, write me, write your queries in the discussion forum. We'll answer it there. Okay. All right, guys, take care. Bye-bye.
Thank you, sir.